So today we are going to be having a look at travel graphs. So travel graphs deal with your distance versus time graphs, as well as your speed versus time graphs, and how we deal with acceleration from that as well. So let us have a look. Travel graphs. Da-na-na-na. Travel graphs. Do. All right. So we need to make sure that we know a couple things about our travel graphs and the quantities we're going to be looking at. So first thing we need to do is we have a look at distance. And we know that distance is the how far quantity. We know that we have time, and time is the how long it takes quantity. And then we have speed, and speed is my how quickly quantity. All right. So we need to be able to relate these to each other. And distance could be in meters or kilometers or whatever other measurement you want. Time will either generally be in seconds or in hours. And therefore speed, if we're looking over here, will be in meters per second, or if we're looking over here, kilometers per hour. So if you're traveling in a car, you'll probably be dealing with kilometers per hour. If you're running like a little trolley or something like that, it will be meters per second. All right. Sometimes if you have something very quick as well, so if you're throwing a ball up in the air, it might be dealt with in meters per second because it's not going to be up in the air for too long. Now, how can we relate these? Well, this dash line, this oblique or forward slash, is relating to dividing. So here we are dividing kilometers and hours. In other words, we're dividing distance by time. Now, in case you are unsure how to calculate stuff like this, we have something that has got a terrible name, but it is something that you will remember. It is known as the idiot's triangle. No, I'm not calling you guys an idiot because I use this as well. So therefore, if I was, I would be calling myself an idiot. So this is the idiot's triangle, and we have speed over here, we have distance over there, and we have time over there. So if we want to calculate one of these quantities, all we need to do is block it out. So if we want to calculate speed, speed is therefore equal to distance, and we use this line as a divide by time. So speed equals distance over time. If we want to calculate another quantity, so let's say, for example, we want time. We cross out time, and that leaves me with distance over speed. So time is distance over speed. And then if you want distance, you cross out distance, and that's speed, time, and this vertical line means a multiply. That is distance is speed times time. All right, most of the time you'll only ever have to worry about this one though. So if you don't want to remember the idiot's triangle, that doesn't make you an idiot. You can just remember this one formula, and there you go. So let's have a look at this graph. This graph is a distance time graph. Now, how did I know that it was a distance time graph? Well, because it told me. No great shakes there. All right, distance on my vertical axis, time on my horizontal axis. So I could have a question that says, this is the distance time graph of a family traveling in a car on holiday. And the question says, when did they set out for their holiday? Well, when did they set out? In other words, when did they start? They started at the very beginning at 7 a.m. All right. Now, if I want to calculate my average speed for the first hour, for example, the average speed is the distance traveled in that time over the time it has taken. So the distance traveled in the first hour is 50 kilometers. The time taken is 1 hour. Therefore, my speed is 50 kilometers per hour. So this line over here, you might then notice as well, this calculation relates to another mathematical quantity, and that is gradient. You'll say, gradient? I've heard of gradient before. I remember I didn't like it, but I remember I've heard of it. Well, what was gradient? Gradient is the slope of my line. And how do we calculate the gradient? We're always told it's change in y over change in x, or rise over run. So we're trying to go from here to there. Rise, run. Rise is 50, run is 1 hour. That is my calculation. So that's all it is. So my speed is actually the gradient of my distance time graph. Well, that's going to come in handy later when we come to our speed time graphs. We're going to see how all of this is actually related. Then they decide that they are going to have breakfast. When did the family decide they're going to have breakfast? Well, breakfast would have to be over here because they are not going any further from home. So your distance is remaining the same because it's flat, therefore they're probably having breakfast. Then they get back on the road and they travel for another 2 hours, and then they hit a motorway and suddenly they speed up. All right. What is my average speed over here? Well, average speed there was 50. Average speed here, well, average speed is again rise over run. So rise is 50, run is now 2 hours. So that would make it 25 k's an hour. What about this one? Average speed here once they're on the motorway or the highway. The rise is 100, the run is 1 hour. Therefore, this is 100 k's an hour. And therefore, you should be able to see that the steeper the line, the quicker that we are going, because it has a steeper gradient. All right, so hopefully no big shakes about that, nothing too unknowing or throwing you off over there. Yes, I did say breakfast. I did not say Brexit. They decided to stop for Brexit and then keep driving on the motorway. That is fantastic. All righty. Then we have a speed versus time graph. Again, how do I know it's a speed versus time graph? Because they told me. So speed versus time, we now have an increasing speed. We need to have a look at the previous graph just so that we can see that the speed here was consistent. This whole thing was 50 k's an hour, and they were traveling at a constant speed, 50 k's an hour, for that entire hour. Here, it's not quite like that. So here, my speed is actually changing. Here, my speed is staying constant, speed changing, constant, speed changing. So we therefore need to be able to have a look at this and say, well, what's going to happen to my distance that is being traveled? And also, what is happening to my acceleration? All right. So if we need to try and remember the triangle as has been asked, I honestly remember it using the units. So I know that speed is kilometers per hour. And therefore it's speed, distance, time. That simple. All right. Now, if I say to you, what is or what was the acceleration in the first hour and a half? We need to say, acceleration? You've never mentioned acceleration before. Well, that's true. But I'm mentioning it now. So what is acceleration? Acceleration is the rate of change of speed. So it's the rate of change of your speed. So you're traveling in a car at 50 k's an hour, you put your foot down in the accelerator and your speed increases, you are accelerating. Suddenly, some dumb oak decides to jump out in front of your car, you slam on brakes and your car slows down. That is deceleration. So what is my acceleration here? Well, my acceleration is the gradient of my line. Simply that simple. So acceleration is going to be the speed over the time. So my speed here, I got up to 90 from 0. And the time, it took me an hour and a half. So it's 90 divided by 1.5. And that should come out at 60 kilometers per hour squared. So your acceleration is 60. Amazing. What is my acceleration here? Well, my acceleration would be 0 because it is a constant speed. The gradient is 0. What is my speed there? My speed is not 0. My speed is 90 for that half an hour. Then it goes back up again, and it's again accelerating in the exact same way it was. And then there's a sharp deceleration there. So we can calculate all of this. Is there a way that I'm able to calculate how far they have traveled, but using the speed time graph? Well, actually, yes. And so much yes that I'm going to use a different color. So this area under the graph is actually going to help us to go backwards and to tell us what the distance traveled was. So how do we calculate the area of a triangle? Area of a triangle is a half base times height. So a half base, that is 1.5. And my height is 90. So we have a half times 90 is 45. 45 times 1.5 is adding on 22.5, which makes it 67.5. So that is 67.5 kilometers. How far did he travel in this bit? Well, that's a rectangle. Length times breadth. So my distance traveled there is length, which is half an hour, times height, which is 90, which will make 45 kilometers. That should make sense because in this time he is traveling at 90 k's an hour. And he's traveling at 90 k's an hour for half of an hour. Therefore, he should have traveled 45 k's an hour, 45 k's in that half hour. What about this shape over here? This is the next big section up to there. How are we going to calculate this? So this is a trapezium, and either you can then calculate the area of a trapezium using the formula, or you could realize that this shape can be broken up into a rectangle and a triangle. Both of them perfectly correct, up to you. It'll be quicker if you use a trapezium though. So there my distance is going to equal a half times the sum of the parallel sides times by my perpendicular height. So once again, I mentioned, in case you've never heard of this before, there's a half times the sum of the parallel sides being that length and that length over there. So it's that one there and that one there, times by the perpendicular height, which is that height over there. So this height is 90, that height is 190. So it's a half 90 plus 190 times by my perpendicular height. That goes from 10 to 12, which is 2 hours. So very nicely, the 2 and the half cancel. And that leaves you with 90 plus 190, which is 280 kilometers. See, very quick calculation, actually. So let us just quickly finish this off. And we can then calculate a distance here. The distance here of my rectangle, that is 1 hour by 190, which makes that 190 kilometers. And then this triangle over here, just block that out. So this triangle over here is a half base times height. The base is 3 hours. The height is 190. So it is a half times 3 times 190. So half of 190 is 95. 95 by 3 is 270, 285 kilometers. So therefore, in total, these people have traveled 67.5 plus 45 plus 190 plus 285 kilometers. And that is 67 and 45 is 112 and a half. 112 and a half, 212 and a half, 302 and a half, 302 and a half, 587 and a half, if I'm not mistaken. It is possible I'm mistaken, but you get the idea that I've just added the 4 numbers. 587 and a half, thank you, Caitlin. 587 and a half. And then if you wanted to calculate the average speed over the entire trip, you would have to take that distance, divide by how long they were traveling, which is from 8 to 4, which is 8 hours. And that comes out at, so that should be 50, 60, 70, 1, 2, 73, yeah. So 73,4375 kilometers per hour. All right. So last thing we need to have a look at is just the fact of how your distance, your speed, and your acceleration are related. So as a summary, distance to speed, gradient. Speed to acceleration, gradient. Speed to distance, area. And if you ever need, which you probably won't, area acceleration to speed is area. And since you guys are doing IG Maths, you should hopefully recognize what calculating the gradient of a graph actually is. And this is the major crux of everything that I'm going to be doing in green. What is the gradient of a graph? It is the derivative. Dun, dun, dun. And then you hopefully should know also about what the area under a graph is. And that is the integral. So somehow a simple little section of travel graphs can actually and is based on derivatives and integration from calculus. Ooh.